Yeah, so my name is Dylan. I am a quantum scientist at PsiQuantum. And in light of trying to bridge the gap between NISQ and fault-tolerant quantum computation, I thought today I would have somewhat of a pedagogical talk, talking about one of the most well-studied algorithms in quantum computing, quantum phase estimation. But describe this algorithm, kind of recast it in a new type of framework or a language. And I should actually clarify that this isn't particularly a new take. I think signal processing has always been a powerful tool in quantum computing, shown by the previous talks. But I think it's still very useful for understanding phase estimation. And so my goal for this talk is for everyone to be in a kind of a place of better understanding of phase estimation by the end of this talk. So when I talk about phase estimation or QPE today, I'm really restricting myself to the discussion of what we call QFT-based phase estimation, using kind of the use of the quantum Fourier transform in the circuit. And the problem at hand is to estimate the eigenphase of U, where I've pulled out the factor of 2 pi so that the eigenphase phi lies nicely in between 0 and 1. And the task at hand is to estimate this phi to some finite bits of precision. I'd say it's an understatement to say that phase estimation is a workhorse algorithm in a lot of fault-tolerant quantum applications. And yet, there is, at least personally for me, there seemed to be a gap between how textbook version of phase estimation, like the one shown here, is often introduced and how we learn it, versus the more recent improvements that we've been seeing in literature. And so let's kind of review how we often learn phase estimation by walking through the circuit. For today, I'm going to assume perfect eigenstate preparation, which I know is a huge assumption, but for the just the case of a more pedagogical workflow, I think it's nicer to kind of pull out and only focus on how the phase register evolves throughout the circuit. So given n phase qubits, or n qubits in the phase register, we first apply all Hadamards on those phase qubits, which lands us into a nice superposition, followed by applications of these control unitaries, or powers of U, such that we implement the right phase kickbacks, and followed by the application of the inverse QFT. And of course, we will measure and get ideas on what the true eigenphase is. But from a theoretical perspective, we often focus on such outcome distribution, the probability of drawing a particular outcome y, and looking at this probability distribution, which can be nicely depicted using something like a histogram, we can say some set some nice bounds or set statements about the expected error, as well as the success probability of drawing an outcome that is close to the sufficiently close to the eigenphase. But for me personally, walking through this math is definitely helpful, but it doesn't give me perhaps the best tools to understand more recent improvements in phase estimation. And so what are these recent improvements? I only list a few here. Some of these categories include what we call window or probe states, really inspired by signal processing as well as quantum metrology. And people have come up with really clever tricks to compile kind of the controlled powers of U in the middle of the circuit to make it more efficient. And the last column can really itself be its own subdiscipline, in my opinion, really kind of the art of how to encode the spectral information that we're going to then query to get an estimate of the eigenphase. And of course, there are many more, but I only show these 3 for today. So here are the proper citations. But the question remains, I still don't really know how to now reconcile all these improvements using kind of the working through the math that I did previously. And moreover, a lot of these improvements are not mutually exclusive, especially from different columns. You can mix and match these improvements to hopefully come up with a more performant flavor of phase estimation. And this is really shown when we're programming or developing code for phase estimation. So on the left is what I thought was initially pseudocode, but I was really writing in Workbench, which is PsiQuantum's quantum circuit simulator code. And this is an example of the textbook version of phase estimation, where you apply an even superposition, followed by the control powers of U, and then the inverse QFT. However, using such structure of code, it kind of doesn't give me a lot of room to incorporate a lot of the improvements that I've just shown in the previous slide. This then would force me to kind of rewrite phase estimation each time to incorporate some of these changes, like windowed phase estimation or bidirectional phase kickback phase estimation, and et cetera. And while a lot of these add new features to phase estimation, they still share a lot of the core structure. And this can lead to a lot of code duplication and make it hard for us to really mix and match these improvements. So this kind of motivates us to perhaps rethink or re-abstract the way we think about phase estimation. So we're going to actually re-walk through the same kind of evolution of the state in the phase register, but now we're going to visualize it in also a graphical form, where I'm plotting kind of the amplitude of the state in the phase register. And I'm essentially just unraveling the state and plotting the basis state of each of the phase register. And so, and for the plots, I'm assuming n equals 3 for simplicity. And so after you apply the set of all Hadamards, you have this even superposition, which you see in blue in the real components. And now it's time to apply these sets of control powers of U. But I'm going to actually say that we're going to use a slightly different notation or a circuit compilation of these powers of U. Instead of using what we often see in phase estimation literature in the textbook case, I note that that's actually an optimized version, an efficient version of a much more naive but easy to understand applications of powers of U, which is shown on the bottom right. For those of you in more fault-tolerant quantum algorithm development, you might notice that this is more like a select-like structure. But essentially, the one on top is removing some redundancies in the circuit, as well as explicitly accounting for the fact that K is encoded in binary. And so once we replace the control powers of U using the naive construction, let's try to understand what's really happening here. So in the first case, what we're essentially doing is checking if K equals 0 and applying the corresponding power of U, which is U0, U to the 0, which is the identity gate. And the next gate would just simply check if K equals 1 and apply U to the 1, and et cetera. So right, you're checking the value of K and applying the corresponding U to the K to the system register. So now let's walk through what happens to the circuit. And for this example, we're going to set phi, the exact true eigenphase, to 0.1875, just for kind of the walkthrough exercise. So we've initialized the register to non-zero amplitudes using the Hadamards. If we apply the first gate, where we check if K equals 1 and apply U to the 0, which is the identity gate, we don't really see any changes in the state vector. But as we check if K equals 1 and apply U to the 1, we see the transformation for the corresponding basis state. And we start to kind of slowly walk through each of these operations and see that we are evolving the amplitudes sequentially in this particular decomposition until we get to the very last query. And so what is the plot that we're seeing here? And the answer is right there on the screen in green, where this is the complex exponential function over K. And I've only just kind of plotted the real and the imaginary component overlaid on the same plot. But there's another way to plot this if you were to put it on different axes as a spiral. But this type of picture that we see here is not really new. We have seen this before, and it's not necessarily in quantum computing. That is, in signal processing, we have some incoming signal, either from nature, like audio, or a man-made signal, like a waveguide generator, and we have some underlying signal. And in practice, we use a digital device to sample or record the signal at discrete times, shown by kind of the round markers here for a complex exponential signal. And then we would take these samples and feed it into some sort of signal analysis, which we'll talk about it more later. But like we see this in digital signal processing, I would say that in phase estimation, the phase register is really labeling the time points, the discrete time points at which we're sampling or rather recording the quantum signal. And in that sense, time is a quantum variable in our context. And the size of the phase register tells us the duration of the time at which we're recording this signal. And so by increasing the number of phase qubits in phase estimation, we're increasing the sampling duration of the same signal oscillating at about the same frequency. So on the left, we see when the phase register uses 3 qubits, and therefore 8 different points of the signal. And then once we add one more qubit, we have now 16 kind of discrete time points at which we're recording the signal. And going back, what does this signal analysis mean? Of course, there are many, many ways to analyze, but for today, we're going to stick with the discrete Fourier transform, or DFT, where we're converting kind of the information from the time domain to frequencies in the frequency domain. And there are many different ways to analyze and plot kind of the outputs of DFT. But today, I'm going to restrict ourselves to talking about the amplitude squared, or the magnitude squared, which is also called the power spectrum. And the reason becomes quite clear, and it's because at the end of phase estimation, just before measurement, we exactly have this square magnitude quantity. So from here on, I'm going to kind of refer to this distribution as a power spectrum of the quantum signal, if you will, in phase estimation. And so on the left, we see kind of the quantum signal. And once we apply the inverse QFT, which implements this time to frequency transformation, we see the power spectrum on the right. And I just wanted to note that as a convention, if you look at kind of the math and the signs that are involved, it turns out that the inverse QFT in this context is analogous to the forward pass of DFT. But if you were to kind of stare at this power spectrum, you might notice that there are kind of 2 dominant peaks about the true eigenphase that are shown by the red dotted line. But there are also these other peaks that are going on away from the expected peaks right here. So where are these probabilities actually coming from? And to understand that, we can actually turn back to kind of the classical signal processing sense, where we have a notion of time-limited sampling of a signal. So consider a sine wave that's sampled at 5 hertz, or 5 cycles per second, and we're sampling from 0 to 1 second. We see that if we were to apply DFT and look at the power spectrum, we see a nice clean peak at around 5 hertz, which is what we expect. But suppose we sample it from 0 to 0.5 seconds instead, and we see kind of a truncation in this sampling duration. And now the corresponding power spectrum has still kind of this dominant peak or mass around 5 hertz, but now there's a wider spread about that dominant peak. So the question is, why do we see this spread? And it's because when we're actually applying the Fourier transform, this process assumes the periodicity of the sample of the signal that you're kind of inputting. And visually, I like to think of this as taking your time-limited sampling and putting them next to each other infinitely. And you can see that there's a huge region of discontinuity between where the 2 samples meet. And you can think of Fourier transform as somewhat of almost a way to reconstruct your original signal using the frequency components. And using that picture, you can see that you need a lot more frequency components to reconstruct the sharp transition. And in signal processing, we call this effect spectral leakage. But luckily, in signal processing, you can reduce the effects of spectral leakage by applying what we call a window function or a tapering function, which is, as the name suggests, just a function that kind of tapers on either side of your sample duration. And you're simply going to multiply this in the time domain to your time-limited sample. And the result is you get your signal kind of still oscillating at about the same frequency, but that's been tapered or enveloped by your window function. And now if you were to take the discrete Fourier transform and plot the power spectrum, you see a slightly broadened peak at about 5 Hertz, but all the other artificial frequencies further away have disappeared. And kind of a qualitative reasoning is that now if you were to kind of do the same picture of putting these samples next to each other, these tapered signals are a lot more periodic than before with this kind of this sharp discontinuity. And I wanted to note that in the original version of time-limited sampling, we're also implicitly applying kind of the rectangular window, which doesn't really taper at the ends of your signal. So let's bring it back to phase estimation. When we're applying the all Hadamards to the phase register, this corresponds to applying the...
Wait, Dylan, can we go back just 1 second?
Yes.
So is this to imply that if we were to take just a little bit longer window and wait for that signal to go back down again, then we wouldn't nearly see that frequency spread that you were talking about before. It's about connecting the two lines and making it as periodic as possible.
Exactly. And if you were to capture kind of another one of these dips, it's kind of like saying your true eigenphase is exactly representable by that time duration, which corresponds to the number of phase qubits that you use.
Yeah, exactly. But,
yeah.
So in practice, we don't know when we're going to be at the top or the bottom.
Exactly.
Right? So we sort of just have to accept, okay, maybe we're somewhere halfway in between. But you've given us like the worst case scenario here.
Exactly.
Okay,
exactly.
very cool.
Yeah, so going back, when we're applying all Hadamards to the phase register, this is like applying the rectangular window by default, just as in the classical case. But now we know that this doesn't have to be our default. We can actually replace this with a unitary that prepares an alternative window state that perhaps has this tapering feature. So for this example, I'm going to use the cosine window versus the rectangular window construction, and apply the same type of series of signal recording operations or phase kickback. And now we kind of see the analogous picture of the tapered window state or the windowed signal state before the inverse QFT, followed by a power spectrum where we see the same type of dominant peak. Two dominant peaks are around the expected eigenphase, but all the other components have been suppressed. And recall that the rectangular window kind of had a very different picture. And I wanted to note that because we're working with probability distributions, not just power spectrum, this kind of says that if we were to kind of suppress the other frequencies, this also corresponds to boosting the probabilities of your dominant peaks, which corresponds to the success probability of phase estimation. And so as a brief summary in terms of windowing, just as we see in digital signal processing or DSP, applying a non-trivial window in phase estimation can reduce the effects of spectral leakage, which in our case corresponds to increasing the success probability of drawing a state that is sufficiently close to the true eigenphase. And I wanted to note that in digital signal processing, there are many, many different window types developed over decades, but they have particular trade-offs, and usually the two things that they often talk about is the width of these dominant peaks versus the rapid decay rate of the side peaks, kind of falling away from the true peak, true eigenphase. And so you'll often see pictures like this, where you take the power spectrum of a window function, and this is how they kind of characterize kind of the main lobe width of the central peak or the dominant peak, as well as the decay rate of the side lobes. And I wanted to show that this picture is no different from what we actually see in phase estimation, just a discretized version. So here I'm showing the power spectrum of when we're using a phase estimation using the rectangular window on the left and the Kaiser window on the right.
Yes.
Yeah.
Perfect. And can you go back to the previous slides?
Yeah.
So when you say that there is a trade-off, so I think usually in quantum phase estimations, we care about the total running time and also the maximum running time, which corresponding to the circuit depth we need. And I'm wondering how the two things affect the total running time and the maximum running time.
Yeah, that's a good question. It's a little bit of a complicated one because I think in my mind, it also depends on your ultimate performance metric. Say that you have something like this confidence interval that sets like the precision window, which will basically set the width of your main lobe. So you better pick a window function where the main lobe width is smaller than your defined kind of confidence interval of your performance metric. And then the side lobes really has to do with the leakage of the success probabilities, which impacts your time to solution or runtime. So I think in that sense, establishing a clear kind of set of performance metrics on phase estimation will kind of dictate the types of window functions that you use. For Kaiser window, this would tune the parameters of that window. And from then on, you could probably make some cost estimate about the actual full QPE circuit multiplied by the number of shots that you have to take depending on the success probability.
Thank you.
Yep.
Just as an observation, the narrower you want this to be, the longer your circuit has to be.
Okay.
Yeah, so in practice, how do you choose between different window types? Do you have to have knowledge about things that you're measuring, or without any knowledge, is there a way to choose that different?
Yeah, I will talk about that in the following slide, but yeah, ask me again if I don't answer your question. So yeah, there are two examples where we use the rectangular window on the left and the Kaiser window on the right. Yep.
Yes, sorry. So in the previous example, the cosine window already did like perfect, basically, right?
Sorry?
In the previous example, the cosine window already did very well. Like there are no leakage.
Yeah.
So why would you pick a different window?
Okay, that is a very good question and a great observation. It was kind of a contrived example where the true eigenphase 0.1875 is exactly representable using 4 bits, whereas I use 3 bits in the phase register. And so your true phase lies like smack in between two nearest neighbor kind of bins of this histogram. And in this case, cosine window is known to be kind of the most optimal case. Just like for the rectangular window case, if your true eigenphase lies right on one of the bins, that's like the main option of the window you should go for. So, but then we don't have knowledge of the true eigenphase in practice. So in that case, you want to pick a window that performs well, perhaps on average or in worst case.
I see.
Yeah.
Thanks.
Yeah, one more question. So from Lex's question, I'm realizing that there's some intuition I'm lacking. So you're talking about changing the window function can change the relationship, or can trade lobe width and decay. So, and then Lex mentioned, also choosing longer times should, I want to say like narrow the lobe width.
Yeah.
So could you just help me understand the relationship between choice of window, time, total time, and then lobe width and decay?
Yeah, so I think of like the longer kind of evolution or deeper circuit as adding more phase qubits to the phase register, which helps you kind of basically come up with an estimate where the error between the true eigenphase and your nearest bin gets smaller, right? Of 1/2 to the n or n plus 1, depending on how you define success probability. But even then, using a rectangular window for like a large n can still end up in spectral leakage, depending on kind of even in that small resolution where that true phase lies in between kind of the two nearest neighbor bins that surrounds the true eigenphase. And so I think of the choice of windows as kind of a way to boost that extra bit of success probability that comes from the fact that we're discretizing this phase register into, right? Because in practice, if we had infinite phase qubits, then we can always almost exactly kind of resolve the frequency that we're trying to estimate. But in practice, we have this discretization because of the finite bit register. So this spectral leakage is also called bit discretization error. And when we're given that kind of restriction, I think we will always usually have some degree of spectral leakage. And windowing can kind of improve upon that.
Okay.
There are also extra tricks that you can play in conjunction with window functions. So in Nielsen and Trong and other works, there are also strategies to kind of boost your success probability of phase estimation to an arbitrarily high number by basically adding on some number of additional phase qubits, and then applying like those series of control U's on the total number of phase qubits, but ignoring kind of the number of qubits that you've added and only measuring out some baseline number of phase qubits. So that's a way to do it. So you can kind of use window functions and that technique to kind of boost your success probability of a peak that is still off by some amount of error because of your finite bit phase cube register size, but it's still kind of your best estimate scenario.
Okay.
Yeah.
Maybe I can clarify what I meant. For the narrow window function and frequency domain, in order to achieve that, you need it to be long in its conjugate domain. And that means you need more phase qubits in order to be able to have that support, in order to be able to make one. That was the observation I was trying to make.
Yeah, and I will just say, maybe I will talk about this in a little bit, but kind of the more tapered or sharply decaying your tapering function is, the deeper the state preparation circuit for the window function. Yeah. So, right, let me try to get on this. So two scenarios using the rectangular window phase estimation and the Kaiser window. On the left, we see kind of one end of the trade-off where we have a fairly narrow main lobe, where the main lobes are consisting of these two kind of nearest neighboring peaks about the true eigenphase, but all these side peaks are decaying rather slowly, especially compared to the one on the right. We're now here using the Kaiser window. The trade-off is that we have a slightly wider main lobe consisting of 4 peaks, but all these side peaks are decaying at a much faster rate than the one here, where I'm plotting on this consistent Y scale, and signal processing people love to plot things on the log scale for the Y-axis. So this is what I also did to be consistent. And if you were to look at the time domain representation of the signal, this is kind of a non-tapered rectangular window and a tapered Kaiser window. And I just wanted to note that now, if you were to kind of go back to signal processing literature and look up all these different window types, you know exactly what these plots represent. These are the same things, just analogous. So in the green is the representation of the window in the time domain. And on the right is just this discrete or Fourier transform, and showing kind of these kind of lobe picture or representation of these window functions. And so to go back to your question of like, when should we choose certain windows and why, is exactly my open question. So I'm trying to kind of leave room for some of these open questions that still exist within the field. I think this really depends on the performance metric that you assign, as well as their specific values. And in those contexts, it's still an open question what the best window function choice is. Of course, in quantum computing, we also want to account for the cost of the window state preparation as well. Yeah.
This is a purely classical question, right? Like has nothing to do with quantum. Okay.
Yeah. So I think I'm a little confused about this open question because I do remember in one of Dr. Barry's papers, they claim something like the windows is the optimal choice for that window function.
Yeah.
So I want some clarifications.
Yeah, good question. I also have that same question for a while, but because before Kaiser window was kind of the state of the art, people always used the sine window because that was known kind of optimally from actually metrology and interferometry type of argument that it is optimal for minimizing the whole level variance, which is another type of kind of a measure of spread in the eigenphase measurement distribution. So it seems like depending on what performance metric you're using in the error analysis of your overall fault-tolerant quantum algorithm or application, the choice of window could be a little different.
Okay.
Yeah.
So you mentioned that Halil variance was optimal for the sine window. What was optimized for the Kaiser window?
It's this idea of if you're considering some sort of like a confidence interval and you want to reach a particular confidence level, then I think it's in order to kind of like boost the success probability in that scenario, people seem to say that the Kaiser window with a certain, Kaiser window is also parameterized by this bandwidth parameter alpha or beta, and that has a very specific optimal value in order to saturate that performance metric. Yeah.
Should provide like a example actual number for like depending on the choice of these windows, like how much, like what kind of factor does the accuracy or the runtime be affected? Like it's like order of magnitude thing or like a factor?
Well, it depends. So the rectangular window, in the worst case, we show that the success probability is 81%. If you call the success probability at, if you say the success probability is the total amount of probability of the two nearest neighboring peaks, the minimum value for rectangular window is known to be at around 8 over pi squared or 81%. So if you kind of make this like time to solution argument and you can somehow use a different window function in a particular scenario to boost it to 100%, then you can kind of compute out, even measuring, like it depends on the confidence level you select, but even if you measure save one shot in the Kaiser window case, that actually saves like around 2 times in terms of time to solution if you have to make 2 shots in one case and only 1 shot in the other. Yeah.
Sorry, just like a loose question since you mentioned metrology here. Can you think about like Fisher information of different windows? Is that like a precise thing you have thought about?
I think I've definitely seen kind of discussions around that, but I've not personally looked into that.
I guess I don't know very much about classical signal processing, but I imagine that a lot of the time they're looking for like a set of frequencies, like looking at a molecule, whereas here there's one frequency. Does that like simplify the problem? I imagine that studied classically like 60 years ago or something.
Well, in practice, right, we still have multiple peaks because if we assume that we have an imperfect eigenstate, it's really, I think of that as like having a probability distribution of probability distributions. So in practice, I think it's definitely, you're basically sampling from this like kind of multimodal type of distribution in practice. And I don't know if it's any easier, but I will say that because the signal form is the complex exponential to begin with, and the Fourier transform of that is a discretized version of the Kronecker delta function, I think phase estimation is really nice in that that's why we see that the lower bound for the success probability is already at 81%, which is quite high.
There's another thing that they use, like, I guess, experimentally, this like phase locking, where you have like a, suppose you know already pretty accurately what the phase is.
Yeah.
And they like run some signal and they kind of allows them to much more accurately.
Yeah, exactly.
Yeah,
That's
something
definitely.
you can use here as well, like if you
I believe so. It hasn't been as fleshed out yet, but I definitely think that's something I also thought about, but never fully fleshed out. But that definitely sounds like a technique you could possibly use. Of course, you will have to just make more shots at different kind of like, because you're kind of artificially perturbing kind of your system to see kind of the responses and trying to extrapolate like where the true eigenphase is based on that, right? Something like that. Yeah.
So this is a step back question for me from windowing. So great, we're saying that there are cool DSP things that you help us understand QPE. And if I squint and maybe speak not precisely, QPE is just DSP, but the signal comes out of the quantum computer. Right? There's a signal, the autocorrelation is propagated on the quantum computer, the Fourier transform happens on the quantum computer, and then you get your frequencies off. Or maybe I could just create the autocorrelation function on a classical computer if I could just evolve that big matrix H. If I could evaluate e to the minus HT, I could just do that on a classical computer. I could write down the signal, and then I could take the Fourier transform of it. So then, under that, perhaps naive understanding of what the quantum computer provides benefit because evaluating e to the minus IHT is wrong. It's hard. Because I don't know how to do that on a classical computer in polynomial time. But for certain Hamiltonians that we care about, the Fermi-Hubbard or whatever, there's a polynomial number of operators. I can do that on the quantum computer in polynomial time. Is that too naive? Is that correct? Is there another benefit on top of just evaluating the time series?
I think broadly that is the right intuition, but just reminding ourselves why it's easier, because just looking at the raw numbers of points, if we wanted, this is just a simple example of when we have 4 qubits, 4 qubits and just 16 discrete samples. But suppose we needed a ton of these, like 2 to the, I don't know, some large number of points to resolve your signal, then on a quantum computer, that's still fairly cheap in terms of the number of qubits.
I mean, doesn't since you have to do u to the 2 and u to the 4 and u to the 8 and u to the 16 and u to the 64th and u to the 128th, the time you have to evolve to grows sort of with the number of basis states. And so there's some you get more basis states, but the time to evolve is similarly growing, and so there's not like an extra compactification there. And so you're sort of growing, you're getting exponentially more basis states, so you get more signal, but you're doing exponentially longer gate depth in simulation. So I don't know that doesn't seem like a strict win to me. Maybe it's a space win. Space wins are good, but not a time win.
Yeah. I guess that boils down to a closer analysis of how efficient can we apply each of these U's? Are there compilation tricks that we can use to kind of lower the cost? But in terms of the query count, I agree.
I was going to go back to Michael's question for a second. So I think there's, in like the classical world, if you know you only have one peak or a small number of peaks in the frequency domain, right? There's a lot of tricks. Like, for example, you can fit some curve to it to like determine the position of the peak to like a finer accuracy than your spacing between your bins. And I think the like quantum analogy of that, okay, so if you had a perfect fault-tolerant quantum computer, I think that's like not a smart thing to do. Instead, you just increase your evolution time to like make the peaks more narrow. But there is a class of like FTQC algorithms where you do things like that. You like draw a bunch of samples and then do some post-processing to try to figure out where
the problem with that is, and naively, like our intuition is increasing the evolution time, and like the time evolution operator should create better resolution. But I don't talk about it too much here, but there's also this effect of aliasing, which means kind of if your signal's like native frequency is quite high, but you're undersampling the signal below some duration of time, then your eigenphase that you read out is ambiguous up onto some multiples of 2 pi. So you have to kind of like do this balancing act. Yeah. Okay. Yeah, so we saw this, an example. Yeah. And so at this point, how are we doing on time? We can update our picture phase estimation. Instead of thinking about it as just applying all Hadamard's on the phase qubits, we're really applying this implicit rectangular window. But we're not restricted to this picture. We can just apply a particular window state preparation circuit. And we've shown that the inverse QFT in this case is really about converting your quantum signal in time to the frequency domain. And the last remaining piece is kind of the middle portion where we're recording the signal. And as a quantum algorithms engineer, one thing I have to worry about is reducing the cost of this, often the most expensive piece of the algorithm. So I'm going to focus on this part. And so I'm again going to kind of replace this construction with this naive construction for a moment to see that in this picture, we can see that most of the cost, or a lot of the cost, comes largely from applying the maximum power of U, which becomes a lot clearer in this picture. And to motivate a particular trick from literature that can cut the number of queries by a factor of 2, we're going to go back to the signal sampling kind of picture. So this is, again, the 3-qubit case of the phase register just before the inverse QFT, where we showed that depending on the basis state labeled K, we're applying the phase kickback operator U to the power of K. But theoretically, what if we were able to shift the signal in time? So instead of sampling from time from 0 to 7, I say let's try to sample from times -3 to 4. And so if we kind of follow this logic of applying the right corresponding power of U, in the shifted case, we would expect to just apply powers of going from -3 to 4 instead of 0 to 7, where you might notice that the maximum absolute value of power of U is approximately halved for this case. And theoretically, why can we think about doing this? Is because in signal processing, this is also a known fact, that the Fourier transform of a time-shifted signal, where the time shift is this constant T0, is equal to the Fourier transform of the unshifted signal times a global phase that depends on the time shift T0. And we know that since what we really care about is the power spectrum, the magnitude squared, this global phase is just like how we think about global phases in quantum computing, where this does not change the output power spectrum. So intuitively, this translates to phase estimation. And if we can find some way to shift the signal in time, then this just amounts to applying a global phase in the phase register. So how do we actually do this in practice? Is through this trick called bidirectional controlling of these operators U, where often we only think about kind of the forward direction, where if the control qubit is in the 1 state, we apply U. But in this case, we think about also making use of if the control qubit is in the 0 state and applying U dagger. So you're applying kind of phase kickback in either direction. And because of that, we call this often a directional or bidirectional phase kickback. And so if we were to actually implement this in circuit, this is what it would look like, where in the unshifted case, this is our standard textbook phase estimation control structure. And in the shifted case, starting from the second most significant bit, we start playing around with this bidirectional control structure. And if we were to kind of go through the table and work out what is the resulting power of U that's being applied to each basis state, we retrieve the expected table. And I color-coded the basis state, so later if you want to walk through this exercise, you're welcome to do so. But my original intent for this was to lower the queries of U that you want to make. But you might notice that in the unshifted case, you're making the total of 7 queries to U. And on the left, if you assume that the cost of U dagger is approximately the cost of U, which is reasonable, you'll also count 7 queries to U, which doesn't seem to really make sense. What is happening here? And let's go back to the idea of bidirectional control, where we have, in these 2 cases, we're making kind of 2 queries worth of quantum resources. But it turns out that on the bidirectional control case, we can save around, by a factor of 2, the number of queries to U need to make. And this is shown in literature for actual structures of U's that we care about, in qubitization and in symmetric trauterization. For the sake of time, I'm just going to focus on qubitization, where in this case, the U, which is the walk operator, can be bidirectionally controlled by applying an uncontrolled U that is conjugated by these auxiliary operations, control C, which are significantly cheaper than the cost of U. And in the case of qubitization, this corresponds to the controlled reflection about the prep state. And so if we now assume that this type of decomposition works for our hypothetical case, then in fact, if we were to shift the signal in time and optimize it, we make 4 queries to U, which is what we expected. So saving around 2 times the number of queries. And so it's been known in literature that this trick can save almost a half number of the queries required for a given precision. But this type of signal processing picture really helps you understand why this happens. And this is because you're shifting your signal in the time domain, which does not change your power spectrum. And so to take a step back and abstract phase estimation, today we kind of walk through how textbook phase estimation is taught and how that really dictated how we write code and how limited in extensibility it can be. And so instead, perhaps a new type of abstraction that we think about, if we should think about, is this signal processing picture with this window state prep, followed by recording of their signal, as well as the time to frequency transformation in order to get your power spectrum. And I've explained just 2 of the many connections you can make. So windowing can reduce the effects of spectral leakage. Bidirectional phase kickback is just time shifting your signal to save on the number of queries. And just to mention, there are many more connections to be made. So an open question again is, how can we further leverage ideas in DSP, digital signal processing, to better understand and further improve upon this flavor of QFT-based phase estimation? And so I've said a lot of these summary points, but I hope this served as perhaps a better pedagogical tool for reintroducing phase estimation. I would love to get your feedback. And again, I think there are many ways to probably further adapt ideas from signal processing to improve phase estimation. And the last point is perhaps it will be interesting to see if we can go beyond phase estimation and reframe other quantum algorithms in perhaps a different way. That could be helpful for generalizing. That could help really with the programming of the quantum algorithm and eventual deployment. I know Katharina's talked about one of the challenges being mixing and matching different improvements, and having a more general framework for different pieces can help with that. And so I want to thank you guys for your attention, thank my collaborators, especially Will Simon. And there's an upcoming kind of pedagogical piece, or a handbook, if you will, on a lot of this work, where I connect more ideas like qubitization, but also talk about other signal processing phenomena like zero-padded signals and aliasing. And yeah, so stay tuned. Thank you.